Hello guys, so example number 3, beams, slope deflection. What is the difference here? Where is the difference? Well, the difference is that in the previous example we had to use, we didn't have to actually. It was very convenient if we use the simplified formula, the modified formula, because the ends we have pins and rollers. In this case we don't have pins and rollers, and if you realize the degrees of freedom, or I mean the degrees of indeterminacy are more in this problem. In the other problem we have only 1 degree of indeterminacy. Now you have 3, 6 here, 7, 8, 8 minus 3, 5. This is a statically indeterminate of the 5th degree. Imagine doing this using force method, virtual work, deflections, compatibility equations, I don't know. Imagine that we have to select 5 redundant and don't eliminate those 5 redundants, apply the correction, create a huge system of equations, and then solve it. Now let's see what happened here if we use slope deflections. The first thing that I'm going to do, just to get rid of that and don't complain with that and don't deal with that, is calculate the EI. I know the EI is constant everywhere, and this is my value for E and this is my value for I. So 7 means 7 times 10 to the 9 Pascal means Newton meter square, multiplied by this 800 times 10 to the 6 millimeter square, millimeter to the 4th, I'm sorry. And if I want to convert this into meters to the 4th, I'm gonna multiply this by, I'm gonna divide this by 1,000 to the 4th, because 1,000 millimeters to the 4th are the same as meters to the 4th. And then I have this and this cancel out, 2 of these cancel with this force, and it's 2. And then I'm going to get an EI of 56,000. It was actually 56 million Newton per meter square, but I'm gonna express it in kilonewton because my forces are in kilonewton. So 56,000 kilonewton meter square. Do that at the beginning. Be sure that is correct. Spend, I don't know, 2-3 minutes doing that, but do it correctly. So going back to our formal steps, the first thing will be compute the FEMs. FEMs doesn't mean finite element models. FEM means fixed end moments. And then we go to the tables that we have in the back of the book. You see, this is continuous and continuous, because this is continuous here, right? And this is fixed. So it's gonna be this type of formulas that we're gonna use. Positive in the left, negative in the right. If we use the convention that I'm using, there are people that use the opposite, but let's focus with this convention. So we use this, and it's the same for this, and it's the same for that. I mean, the same formula, and even the same moments, by the way, because these two spans has the same load and the same length. Now for this other, for CE, then we have to use this one here. You see, fixed, fixed, continuous, fixed, and the load is at the center. If the load is not the center, it's not at the center, I will use this, or I can use this and say that A and B are the same. But why I'm gonna do that if this is simplified? So I'm gonna use that once again. In this side positive, in this side negative. So just apply the formulas. Remember, this is the table. So let's start. FEM for AB, and everything else, let's say FEM for this one is gonna be negative WL squared divided by 12 and WL squared divided by 12 if you use this convention. And the moment, it will be, I'm sorry, it's the opposite, right? Yeah, positive and negative. So it's gonna be like this, and it's gonna be like that. Yeah, positive and negative. So let's do that for AB. If we do that for AB, then you're gonna have 20 times 8 squared divided by 12, 106.6 kilonewton meter. If we do now for BA, it's going to be opposite of that, which is this side. If we do BC, this one is the same as this one. We're looking at this side, right? So it's going to be 106.6. And for CB, it's going to be the same as BA. You use this. And the only thing that we have to do now is the other part. What is the other part? This one here. For this one, you have we have this situation. The load is here. So this moment and this moment, if it's the same length, this is length and this is L divided by 2. Remember, we're using this one here. So it's PL divided by 8. That's it. Positive and negative. So we can calculate FEM for CD is going to be equal CE, I'm sorry, not CD, is going to be equal to 60, and the FEM for EC is going to be equal negative 60 kilonewton meter. Done. This is what I like about this method, is that it's standardized, at least the part for beams. The only thing that you have to be really careful is with the when you have the psi value and you have displacement. And don't worry, we're gonna do that with frames and you're gonna have fun. Okay, we finished with this. Now what is the next step? The next step is apply the slope deflections. The slope deflection equations. And what are those equations? Well, the equations are like follows. The moment AB, remember this is the long equation that we discussed in the intro, not the simplified. 2EI divided by L times 2 rotation at A plus rotation at B minus 3 times psi, which is the angle of the chord, plus the fixed end moment AB. And if I use moment BA, it's going to be 2EI over L, and it's going to be here 1A plus 2B minus 3 this plus FEM BA. It's the same equation, you just switch the indices, that's it, the sub indices. So let's start with this one and let's apply that for AB. Moment, these are the equations. If you are gonna do BC, it's the same, just change the sub indices, and same thing here. So sub indices, indexes. AB equals 2 times EI, 2 times 56,000 divided by L, which is 8. Now we have kilonewton meter squared divided by meter. Now we have kilonewton meter. Perfect. 2 rotation at A plus rotation at B. There is no differential settlement between both of them or displacement, so that means that that is going to be 0. However, this is the point that that you have to be. I'm gonna put it here, and I'm gonna explain you this. Plus, let me put here the fixed moment AB, and the fixed moment AB is 106.6. Now look what happened. And this is what you have to pay attention. And somebody asked me the other day, how do you know that? Because you should know that. It's not how do I know that. Everybody that is at this level should know these things that I'm about to tell you. Because this is a fixed support right there. The rotation and the fixed support, whenever you have a fixed support and you have a load, this is the original shape. If you put a load, the rotation here is going to be 0, as well as the deflection, because it's a fixed support. You're not going to have rotation at that point, meaning this value is going to be 0. And not only that, that value is going to be 0, and I already say that this is 0 because there's not differential settlement or relative settlement, relative displacement between the 2 points. Then this whole thing, MVA, the whole thing becomes NAV is 14,000 rotation at B plus 106.6 MAV. Now if I want MVA, well, if I want MVA, I apply this equation here. Now look what happened, and this is once you start getting practice of doing this, then you are a little bit faster, because look at this and look at that. What is the difference between this and that? This is 0 and this is 2 times, and this is 0, and the other thing that changes is this, which before was positive, now is negative. So this one is going to be 28,000 rotation at B minus 106.6, and this is BA. You see? Now let's go and let's calculate now BC. MVC equals 2 times EI is the same, 56,000, divided by L. L is the same. That I'm just doing this because I want to show you, but I don't have to do that. I could just go over the equation directly and do it, but I'm gonna do it. Times. Now let's look what happened with the rotation at B. This is a continuous support. In that support, you're going to have a rotation. How do you know you have a rotation there? Well, because obviously that was from a previous example. Don't even try to compare this with that. But you see, this is a continuous support here, a continuous beam. Then you have a moment there because you have a rotation. At the ends here is different. You don't have the moment, but you have a rotation. But you see the rotation here in the continuous support. This is the rotation. The slope of that diagram is the rotation. So yes, wherever you have a moment that is not a moment diagram that is not flat in that part, you have a rotation. So yes, you're gonna have a rotation in that point. So meaning, if you have a rotation in that point, these two values are gonna remain. So what is gonna be this value? This is gonna be 2 times delta B, theta B, plus theta C. I'm just changing A, B, B, right? B, B, C, C. This is 0, plus the fixed end moment BC. Fixed end moment BC is 106.6. And then you can put it here. Moment BC is equal to, that was 14,000 times 2 is 28,000. Theta B plus, now it's 14,000 theta C plus 106.6 MBC. Now if I want to calculate now MCB, well, MCB is going to be the same, but now this switch, and this also is negative. So it's going to be 28,000 rotation at C plus 14,000 rotation at B minus 106.6. And now you have this other one. What else? Now we have to calculate the last one. What is the last one? Rotation CD and DE. So if we want to calculate the moment CE, the moment CE is going to be equal to 2 times EI over L. How much is that? 14,000, right? 14,000. I'm gonna put the value, well, 2 times 56,000 divided by 8 multiplied by 2 times rotation at C, 2 times rotation at C, plus rotation, that would be rotation at E. How much is the rotation there? 0. Why? Because it's a fixed support. Fixed support don't have any rotation. Minus 3 times 0. Why? Because we don't have a residual displacement or differential or relative displacement. So it's going to be only this plus, now is, instead of being FEMAB, it's going to be FEMCE. FEMCE is 60. Now you have moment CE equals 28,000, rotation C plus 60. There you go. And moment C, moment EC, which is going to be the opposite, then that moment EC is going to be, now what is going to happen here if I say moment EC? Moment EC, this is going to be the same, which is 14,000. Now this is going to be 2 times rotation at E. The rotation at E here is 0, plus rotation at B, which exists. Rotation at B, no. Rotation at C, because I'm doing CE, right? Rotation at C exists. Rotation at E doesn't exist. So this is going to be 14,000. Rotation at B. Sorry, rotation at C. Rotation at E is 0. Rotation at C minus 60. And that's it. And that finished all what we need here. Now we're going to go with the same problem, because if you realize we have all of these equations here, bunch of equations. Now, how many unknowns? 1, 2, 3, 4, 5, 6, 7, 8. How many equations? 6. We need 2 extra equations. Where do we get those 2 extra equations? We get those 2 extra equations by doing equilibrium. Now if you look at the joint B, when you look at the joint B, the moment BA plus the moment BC has to be 0. That's another equation. I'm going to number these equations. So 1, 2, 3, 4, 5, 6, 7. And if you look at the joint C, moment CB plus moment CE is also 0. And then you have 8. And you're going to say, oh, but I have to solve a system of 8 equations with 8 unknowns. Yeah, you do have to. But not really. Why? Let's apply this. So if we apply in the equation 7, MBA, every time that I say MBA, remember my daughter because she did an MBA. MBA. No, that isn't the only time that I remember her. But 28,000 rotation at B plus who is there? Nobody. AB, where are you, AB? Plus 106. It's not AB, it's BA. What I'm talking about, BA. Okay, here. No. This is AB. This is BA. BA. Yes, correct. Yes, correct. Okay. Yeah, it's 28,000 theta B minus, there you go, minus 106.6 MBA plus MBC. MBC is 28,000 theta B plus 14,000 theta or theta C plus 106. What I'm copying? Ah, here, yeah, 106.6, and this is. I just want to be sure that this is correct because I don't like redoing problems. And that has to be 0. So then we can combine this, and then you have 56,000 theta B plus 14,000 theta C, and this is negative positive equals 0. And if I divide this by 4, by 14,000, then I can get 4 times rotation at B plus rotation at C equals 0. And you can call this equation equation 9 if you want to. And now we apply this one, MCB, MCB. That's why I don't sing, obviously. One time I remember I sang and I made a lot of money. People pay me a lot to get out of there. Far away from there. Bad joke, I know, but I'm tired. I'm alone. What can I do? MCB, 28,000. So this one correspond to this one. Now I'm gonna do that. 28,000. The theta C plus 14,000 theta B minus 106.6 plus, remember this is this, which is that MCB, plus MCE. MCE is here, 28,000 theta C plus 60 equals 0. And now we can work this, and then I have 56,000 theta C plus 14,000 theta B minus or equal, if I pass this to the other side, 46.6. And if I divide this, I can divide it if I want to, but I don't want to. I'm gonna call this equation 10. So then what you can do is that you can substitute here this, say that theta C is negative 4 theta B, and then you put this into here. You know, the majority of the people just solve it and that's it. I'm working it with you. And if you get bored and you know how to solve it, teach me, because I always mess up. And then you can solve for that. Negative 2.2 times 10 to the negative 4. And once you have that, you can substitute this into here, and then you can calculate theta C as 8.8 positive times 10 to the negative 4. So now we have these two. Now we can start calculating moments like crazy. We can come here and start with MAB. MAB is 14,000 times this theta B plus 106. So that I have it in detail, but I'm not gonna do it. I'm just gonna put the values here that I got. MBA negative 112.8 kilonewton meter, and I'm just not going through all of them in detail because I don't want to spend so much video time doing this, and you can just stop the video and practice, which it doesn't hurt you. NCE. What am I missing? Well, MBC has to be MBC, and MCB has to be, what did I put here? 112. MCE. Yeah, MCE is that, so MCB it has to be the same thing here. So this is negative 84.8, and NEC is the last one over there, so MEC is negative 47.5 kilonewton meter. 1, 2, 3, 4, 5, 6. Now keep in mind something, you might have errors here. That's why you have to try to work with the maximum amount of decimal places. And you don't work with that, it's a calculator, right? So don't be lazy, because then you're gonna have huge discrepancies here, differences here, and then you have to explain, at least to yourself, oh, is that an error, is that a rounding error, or is there are different moments, which one is the correct one? So try to keep it simple. Now what do? After you have this, you have all of those moments, I'm gonna copy this beam again, and I'm gonna make a cut of that beam. So I'm gonna get this beam, and I'm gonna do this, look. This is A, and then I'm gonna put the span here. This is A, this is B. Support B, I'm going to put it here. This is going to be BY, and then this is going to be C. Support C, CY, and then I'm going to do the last part, which is here, and this is the support E. Now here I have a force of 60, this is 20 and 20, and the distances are 8, 4 and 4 meters, of course. Now let's start putting all the values that we got for our moments. All the values that we got for our moments, let's put the values over there. Moment AB, positive 103.5. Moment BA, negative 112.8. Moment BC, positive. You see, these two must be the same because they are sharing the same joint, one positive, one negative, summation has to be 0. 112.8. Moment CB, negative 84.8. Moment CE, positive 84.8. And this one negative 47.5. And those are just the beams. So I'm just doing this because you can use any method that you want to, you can use any numbers that you want to, any methodology, but I like to do something like this. I can to say, oh, this is gonna be VA, which is the same. This VA gets transferred here, and this is the reaction AY, so these two values are gonna be exactly the same. Now this one, I'm going to call this V at B in the left, so BBL, that's what I call it, which is going to be transferred here, and this is going to be BB to the right, which is going to be transferred ultimately here, meaning the summation of these two is going to give me the reaction in BY. Now here same thing, this is going to be VC to the left, this is going to be VC to the right, and this is gonna be VE, which is EY. That's basically it. That's what you have. Now, what do you use this for? Because now you can go and start working and calculating your unknown forces. How? For example, I can go here and start this and say, okay, summation of moments here. And I'm going to copy it one by one because this is just to explain you. But if you are in a rush, you can do one example and that's it. And the rest of them you can solve it in the calculator. If I do moment here, what do you get? Moment at B in the left equals 0. Like that. You get this one, 103.5, positive. 103.5. And then you have the force coming from this here. What is that force coming from that one? Well, let's work with this one. Negative 8 VA. Now this force, 20 times 8 times 4, positive. 20 times 8 times 4, positive. Minus this value here, minus 112.8 equals 0. From here you can solve for your VA, which is the same as AY, 78.03 kilonewton. This is neat. I very much like this method, really. However, the next method is gonna blow your mind. And everything that we did here, we can solve it in half a page, maybe. Okay, so now we can do summation of forces in the same one. If I do summation of forces in Y equals 0. Now I know this one, right? I can calculate VA. So VA minus 20 times 8 plus BBL equals 0. So now I can calculate BBL, and BBL 81.16 kilonewton. Now we proceed and we go to the next one and we do summation of moments at CL right there. Summation of moments at C in the left side equals 0. Then what do you get if you do moment here? You get 112.8 positive. 112.8. 112.8 minus this VAR times 8 plus, remember the Alamo, this one here, 20 times 8 times 20 times 8 times 4 minus this 84 minus this 84.8 equals 0. And then we can calculate the shear at A to the right, or shear to the right of A. Why VAR? This is not called VAR. This is called VBR. I don't even read my own. VBR. Okay, so VBR is going to be equal to 83.5. Now, VBL is this force that is transferred there. VBR is this force that is transferred there. Guess what? If we get these two, and we add them up, that's going to be VY. Because it's like doing summation of forces in Y at the joint. So that is going to be equal to 164.6 kilonewton VY. So now we already know this, we already know that. We need to find one more and our problem will be solved. So now, do you think we're gonna invent something again? No. Well, summation of forces in Y in the same part. So you have equals 0. So you have BBR minus 20 times 8 plus VCL equals 0. And then we can calculate VCL as 76.5 kilonewton. And last but not least, we can do summation of moments at here. What is here? E. But I didn't call it E, right? Yeah, I call it E. equals 0, and then you have that. And if we do summation of moments at E equals 0, then you have positive 84.8 minus VCR. What is a VCR? A VCR is a video system. VHS, Betamax, and that tells you my age. VCR times 8 plus 60 times 4 minus 47.5 equals 0. VCR equals 34.6 kilonewton. Summation, summation, summation. Now if I get these two, once again, and I add them up, this is one, this is the other one, it's gonna give me CY, and CY is 111.16 kilonewton. What else? What else? What else? Summation of forces in Y. Summation of forces in Y. I can do that, or I can do it in the whole beam. It's the same thing already, because I have every single other value I already calculated. But I'm gonna do it here. So I have VCR minus 60 plus VE equals 0. So VE, which is equal to EY, is 25.3 kilonewton. And with this, my friends, ladies and gentlemen, boys and girls, Dr. Zorin proudly present shear and moment diagrams. Yeah. Diagrams. I see diagrams, shear moment diagrams in my sleep. I don't like you to do that. I wouldn't advise that. You know what I'm singing, or what I'm doing, that humming? Because you don't have any other choice. It's either listening to me or muting. So I have what is called a captive audience. And you should comment, by the way. You should say, oh, amazing. You should change. You should stop teaching and becoming now a singer professional, or a professional hummer. I don't know. Okay, now we have that. There you go. Shear, kilonewton. Moment diagram, kilonewton meter. There you go. And this is all we need to do this drawing. VA 78.03. I say 03. I lied to you. This is not 03. This is 83. 83. Stop. Probably you detected it already. You're saying, yeah, you better keep singing and stop teaching, because you don't make so many errors. So many errors when you sing. This is 83, but it's a good thing that I did it now. Okay. And this goes, as you can see, this goes up, right? So up here, 78.83. And then here, and this is going to be affected by this load, and it's going to come, and then you find this BBL that is going to push it up also. So that BBL is 81.16, meaning here 81.16, and then this one is the reaction in BY. The reaction in BY is going to be this one, that is going to push this up to this value, DBR, and BBR is 83.5. And then once you have that value for BBR, which is this one here, once again the load is going to be affecting it down, and it's going to reach up to this point, and VCL is going to push it up. So that means that the value here should be negative 76.5. So this can push it up. When I come here, I find the value for this reaction here, which is this one here. Also, is going to pull this from. You can either say that this value is being pushed up by CY, or you can say that this value is pushed to 0 by this VCL, and now VCR is going to push it from 0 to somewhere higher, which is 34.6 periodic. You see, I'm copying the values that I have here. And now, what happens here is going to be constant up to this value, 34.6. And then you have this force of 60 that is pushing it down. And it's pushing it down to 24.3 periodic. 60 minus this is going to be the value. When you see this here, I don't have the detail, but I have this one. I know there has to be 25.3 periodic. So this one is going to be pushed down to 25.3 periodic, and then this is going to be constant up to this point, and then you're going to have the reaction that is going to push it here. So let's make the lines. And now remember, yes. There you go. Now, of course, for the moment diagram, even though I have all the values, I need to calculate these points because those are maximum moments. But I have all the values for moment here. You see these? 103.5, push it down. 103.5, 103.5, push it down. Now, this is positive, this is negative. Remember, please don't neglect infants. Neglect dumb people instead. This is positive decreasing, positive decreasing, positive decreasing, negative increasing, negative increasing, negative increasing. It's going to go up to here. What is this value? This value is going to be 112.8 periodic. Why? Because once I reach this point, which is 112.8 periodic, I'm going to find this moment, and this moment is going to push it up, okay, towards 0, and then this value is going to bring it back again to the same point here. So 1.8, 112.8. Remember, this value can be 112.8, 113. It could vary a little bit because of the decimals that you're using, so don't get too freaked about that. Now, positive decreasing, positive decreasing, positive decreasing, negative increasing, negative increasing, negative increasing, and we go to this value. But we have those values here, 84.8. You see, 84.8. Now what else? Oh my God! Look at that! What I did here. Why didn't you tell me anything? I was so focused onto this. This is entirely and utterly wrong. Oh my God, shame on me. Look at that thing. There's no load here, so this line doesn't exist. This line doesn't exist. This is going to be constant. And I know that you saw that before. And this is going to come down, and this is going to come constant like that. And then this is going to go up. And I realized it now when I was doing my moment diagram. I don't have the results for these moments. Okay, I'm just building this live. That's why I make so many errors. Maybe, yes, I should stick to singing instead of doing that. So this one is positive constant, this one is negative constant, meaning this is going to go up to that point, and then this is going to come down up to this point. And this value here has to be this value, 47.5, which is going to make it up to 0, 47.5. And if you are desperate, yes, okay, go and say yes. But it's not done yet, because we need to find maximum moments. So how do you find the maximum moments? You need this distance. Please tell me, how do you find that distance? I explained that to you plenty of times already. A triangular ratio, yeah, it's a triangular ratio, but you don't have to do that. You are structural analysis people already, so you don't have to do that. What do? You say 78.83 divided by 20. That's gonna give me the value. That is 3.94. That's the value. And this one, this distance is gonna be 81.16 divided by 20, which is 4.06. Or you can say 8 minus that, is the same thing. Now 83.5 divided by 20 is going to give you this distance, 4.17775. And this one here is supposed to be this minus that, so this one is going to be 76.5 divided by 20, 3.825. And that's it, and we know this distance, which is 4, and we know that. Now if you want to calculate this value, you can get 103 negative 103.5 plus this area, and that will give you 51.8. And then you can get this value negative this plus that area, negative that plus that area, that gives me 61.3. And then you go to this value and you say negative 84.8, negative 84.9, whatever value is this, plus this area, and this area is 34.6 times 4. 34.6 times 4 minus this. That's going to give you 53.9, 53.8, somewhere around that realm, because this is 34.6 periodic, so something like that, I don't know. And then this is gonna be this minus this area is gonna bring it to here, which already have is gonna go to there. Okay, that is the whole problem. That might look long to you, but it's actually not. You see, if I show you what we just did, where are you? I don't know if I can find my papers in this mess, but it's not that long. We just did over there underneath here. That was the thing, you see? Fixed moments, calculate that, get your EI, and be sure that is correct. Apply a slope deflection equation. How many? 1 or 2? 1 full equation, 1 modified equation. Apply that to every one of them. Use equilibrium for the joints to find the extra equations. And then the part that is going to take you maybe more time is divide that in this way. But you don't have to be as specific and as detailed as I am. You can do it in your mind, or you can do it in your calculator really fast, and you can get these values. This is the part that is gonna, the enforced member is maybe the part that is gonna take you more time. And then draw your diagram. I want you to repeat these problems, please, but repeat the problems, because in repetition and in practice is where mastery comes into play. So this is the end of our examples for beams, but don't be too happy. Now we're gonna start dealing with frames, which is the next video. See you in 5 minutes.